What is volumetric analysis? Volumetric analysis is a widely used quantitative analytical method. It is used to determine the concentration of an unknown solution by measuring the volume of a solution with a known concentration. This method is also known as titration. It works by measuring the volume of a second substance that reacts with the analyte in known proportions. The first volumetric analysis method was developed by Jean-Baptiste André Dumas. He used it to determine the amount of nitrogen present in organic compounds. Moving on to the different types of volumetric analysis, there are four main methods we use in chemistry: acid-base, precipitation, complexometric, and redox titrations. For our topic falls directly under complexometric titration, which is the specific method used to bind and measure the metal ions responsible for water hardness. What is complexometric? Complexometric titration serves as a fundamental analytical method for examining 1:1 metal-ligand reactions in aqueous media, specifically through the use of ethylene diamine tetraacetic acid (EDTA) to bind metal ions such as copper, calcium, and magnesium. The technique remains a highly reliable approach for determining milligram amounts of calcium in commercial mineral waters, relying on classical indicators like calcine to deliver a sharp color transition at the endpoint.
Imagine water flowing through limestone or dolomite rocks. As it travels, it picks up tiny minerals which are calcium and magnesium ions. The more of these ions it collects, the harder the water becomes. In fact, scientists like Indian and colleagues describe hardness simply as the sum of calcium and magnesium in water. And between the two, calcium usually plays the bigger role because it precipitates more quickly when heated. Now, why should we care? Think about your kettle or shower head. Hard water leaves behind chalky deposits that clogs pipes and even makes soap less effective. On the other hand, very soft water can be too aggressive that will corrode pipes instead. So, hardness isn't just chemistry, it is something we see in everyday life. But hardness isn't all bad. Calcium and magnesium are essential minerals for our bones and muscles. Drinking water gives us a small part of our daily intake. Still, studies show that very soft water may be linked to heart and bone health problems. So, in a way, water hardness is both a nuisance and a necessity. There are two kinds of hardness. Temporary hardness comes from bicarbonates, which you can remove it just by boiling water. Secondly, permanent hardness comes from sulfates and chlorides, and this time boiling won't help. To make it clearer, here's a scale. Soft water is below 60 mg per liter, while anything above 180 mg per liter is considered very hard. That's why we use charts like the one from Philly.club to visualize these ranges. So, how do we measure hardness? The standard laboratory method is complexometric titration with EDTA. This chemical binds both calcium and magnesium ions, giving us a reliable measure of total hardness.
Moving on to our methodology, let's look at the material required for this experiment. We have categorized our setup into the three main sections, which is apparatus, the chemical involved, and the water sample itself. First, for the apparatus, we'll be using a 300 ml conical or air laminar flask which will hold our water sample during titration, a 50 ml burette to partially develop our titrate, a graduate pipette or measure cylinder for volume measurement, along with the standard beaker and a funnel to fill the burette safely. We also have distilled water on hand for raising our glasses to ensure absolute cleanliness. Next, looking at our chemical, we will use a buffer solution calibrated to pH 11 to maintain necessary alkaline condition. Our conjugator of choice is echirochrome black tea, commonly known as the EDTA. And finally, our titrate is a standard EDTA solution. As for the water sample itself, we are testing 50 ml of the tap water. To ensure accuracy, this was collected in a truly clean container beforehand to completely avoid any external contamination. Now, let's dive into the step-by-step procedure for the complexometric titration to determine the hardness of our water sample. So, for the first one is, the sample is being tested with standard tap water collected directly from a medical supply line. Collect the tap water into a clean or pre-raised glass beaker so that to ensure the collection container is completely free for any resident or mineral deposit to prevent cross-contamination of calcium and magnesium ion. Next, let the water sit for a brief moment to ensure no air bubbles are trapped which could interfere with volumetric measurement. Also, As you can see, the procedure setup is we have a magnetic stir, a elemental flask with a stir, and also the burette. First, rinse the clean burette with a small amount of the EDTA solution to remove any residual distill that might dilute the titration. Then use a funnel to fill the burette with the EDTA solution until the meniscus rise slightly past the zero mark. Open the stopcock completely for a brief second to flush out any air bubble trap in the bottom tip. Then carefully align the liquid level to the excess 0 ml starting line. Using a volumetric pipette, make sure exactly 50 ml of the colored tap water sample and transfer it into a clean 300 ml aluminum flask. Drop a magnetic stir bar into the flask. Add 1 to 2 drops of the EDTA indicator solution to the flask. Upon mixing, the solution will immediately turn a distinct white, red, or purple color indicating the presence of the metal ion. Add exactly 10 ml of the pH 11 buffer solution into the flask to establish and lock in the required alkane environment for the reaction. And the next one is place the aluminum flask into the magnetic stir space and turn on the motor to get a steady, smooth vortex going. For the next one, position the flask under the burette tip and begin adding the EDTA solution dropwise into the sample. Watch the color carefully, stop the flow of the EDTA titrate at the exact moment the color changes completely from wine red to a stable clear blue. This sign is show that the titration is at the end point. Read the graduation part on the burette at the eye level and record the final volume of the EDTA consumed. So as you can see in the video, the first run record is the 2.6 ml. Repeat this entire titration process for 5 more times, which is 6 runs in the total, to ensure precision and account from any human error. Or from the video above, so it shows an example of calculate the average volume of EDTA consumed from all the successful runs.
For the example of result, we are analyzing a study published by Applied Food Research in 2024. This graph tracks what happened to calcium and magnesium ions before and after boiling for 30 minutes. Let's focus on a clear example, Berlin tap water. Before boiling, the water is packed with both dissolved calcium and magnesium. However, look at what happened after 30-minute boil. The calcium drops significantly because it forms solid limescale. And look at the magnesium bars, it stays exactly the same height. This means short-term boiling has virtually zero effect on magnesium and it completely refuses to precipitate. So we use a volumetric EDTA titration and watch for a distinct color transition using an EBT indicator. When we titrate our initial unboiled tap water, the indicator binds with the free mineral to turn the solution wine red. Because both calcium and magnesium are fully present, it requires a large volume of EDTA from our burette to force the indicator to change color. However, when we titrate the water after it has been boiled and filtered, a huge portion of calcium has precipitated out. The EDTA quickly binds the remaining ions, so the solution moves from purple to sky blue endpoint much faster. Since the study graph proved to us that the magnesium concentration never changed, it shows that the boiling process successfully softened the water by selectively removing the calcium.
In conclusion, our presentation highlights complexometric titration using standard EDTA as a highly reliable quantitative method for determining water hardness, specifically by measuring the total concentration of calcium and magnesium ions. By utilizing an aerochrome black tea EBT indicator under stable conditions at pH 10, the precise endpoint of the reaction is clearly signaled by a sharp color transition from wine red to blue. Understanding and calculating these values is essential, as managing water hardness not only prevents severe industrial and domestic engineering issues such as scale buildup and equipment corrosion, but also directly impacts public health due to the vital role these minerals play in our daily biological functions.